I expect difficult questions.
Your poetry slam?
Where did you get that wonderful shirt?
I'm going to pass that up.
It should be live now. Let me check back here. Say something into the mic, okay?
I'm saying something into the mic.
That looks pretty good.
Is the level good?
Wait a minute, let me switch over to manual. Oh no, I'm there. I need line. Okay, try it again.
Microphone test.
That's pretty good. Let's go ahead and let me go ahead and play some music.
We need to see how you're.
A little bit more. Go ahead again.
Microphone?
No, loud. Leave it there for a second. Looks good.
You wanted to do a screen test.
Oh, okay, yeah, here we go. Are you hooked up to HDMI?
Is he?
I have it on, it's plugged into the laptop, and I think the computer is. Are you getting anything on that end?
Not yet. Well, you should be plugged into one or two, actually.
Oh wait, okay, now it's detected.
Should be good. There you go.
Oh God, there's math.
You change the formula. There's what? There's regular seltzer water with no flavor in it. Pure. All right. I'll make a little massive when it starts.
I need someone to send me the address for the live stream.
I will do that.
Hello.
Let's write a note up there that we're starting 15 minutes.
Yeah.
I think it's the thing about the computer is so it just became a little This is your video?
Here you go. This year for the travel facilities. Oh, God. Yeah, I guess you said, pull out a window, stare at the grass.
Several times I did. I actually had to turn my head so that my ears were like having the fluid slosh right in like crazy. I get so weak in cars now. It's pathetic.
Yeah. Or what's your partner's name? I forget. They were talking about your set.
Hey, Ralph. What's up? Juggling stuff. Yeah. You going to Knockdown?
We're going to
It's going to be that kind of Knockdown. Everything just got better.
Weird. I don't understand. It's the only trade show I know.
Yeah.
I believe that they sent me to
Yep.
You can interpret it however you want. I truly don't understand.
More fun than maybe easier to deal with than they are. I don't get it if it's mostly just a party or a
I'll say it. I've had some weird moments.
Yeah, oh yeah. It's getting weirder too.
Yeah. I'm actually going back out a few days. I'm not sure where I'm still there. Yeah. Ship for anybody else?
Yeah.
Just moved here.
Yeah, it's kind of nice.
Yeah, I was kind of silent. I like he was way on the south side of the world. Kind of worked his way up from the east side.
Okay, cool.
I'm not going to be around for it.
But I'm gonna make it out there probably another year. I have a system. As soon as I get into work and stuff, I start making more cash.
I don't know what all I'm going to do. Yeah, so creative burnout for that.
Used to make the way
Oh,
up.
it's good. Try to wait so that it's
Oh, yeah, absolutely.
Starts.
Yeah. Cool.
Here you go.
Howdy,
Hey,
Dale.
what's up?
Good to see you.
Good to see you.
I don't know if you remember me. Roger was working on
Yeah.
We went to Pizza Arcade and you really done the place up.
Yeah, remember that? Yeah,
Oh,
that
yeah.
actually happened.
Oh, yeah.
Hey!
No, I did not want to remember it.
I can't believe you didn't throw us out.
Oh, yeah.
Oh, man.
great.
Yeah.
You were the life of the joint.
Yeah. Servers absolutely hated us, but, you know,
Oh, yeah.
everybody else thought we were hilarious.
Yeah, it was so ugly. Servers.
I know we should thought we were funny. Where's the recycling slash
Yeah. They won't hang.
Yep.
Basically, like, laid in bed all yesterday. Or, and just like watch murder shit on Netflix. That's what I do. It's pretty good. It's kind of hit or miss. So each some of them are pretty interesting. It's 2 decks in a row. The next one is good. Which is 7 $2 an hour.
Files of them. Oh, no, that dude's voice is just throwing it on about murder. Listening to it. Do you have like a cold kind of thing?
It's I've been working on that. The decay, filter decay is wackadoodle. So it's super simple. And so Brian's in contact commands and everything. And it doesn't make any sense. My gut had read the moments where it's the question. Take care of the moments. So I'm just on top of it because I wasn't doing that.
It's just not the case.
It's like a fixed length, not fixed long, not really fixed short, which is also weird. So there's a count cap, which makes some. The thought's good. So the bias of that thought's good. The transistor is also good. So that. Again, it's super simple, but
I got this doing there. It's broken if you're a mod.
they want that pizza on the chemical engineer. Shit show of things. Reminds me of we ever saw this last master modules.
I never
It's
saw
also the shit show of them. It's so bad.
I think there was laughable. There used to be, you had one in your case once.
you guys had a difficult time getting in here?
Yeah.
So sometime around 3, when it looks like a good time to do it, I'll run home and let you know.
Yeah.
On I-5 South,
Yeah.
the northbound lane, easy as a breeze. There'd be just like car. Then you look outside in your lane and it's so much so that it's like stop and go. So the whole time, you're only averaging about 28 to 30 miles an hour.
My buddy had the same problem. He just came from Seattle and he was on a bus. This was like a 3-hour ride. It took 6 hours.
Yeah, that sounds about right. Is he on the Gold Bus?
I don't know what it was.
Talking into the mic one more time. Does it work? Does it hurt? Talking again. I am talking again. The man keeps telling me to talk. Now? Okay, we are here at Modular 8 in Portland, Oregon, where the character of the space has changed a bit in the last few months. There's now an abundance of classic video game paraphernalia strewn about the space. So, I've noticed that Phil has been acquiring some more interesting pieces, including one very dear to me, the Atari 7800. So I thought I'd come down and discuss some of the unique qualities of the sound devices that live inside these game consoles. We're going to be discussing some of the most basic tone generators, starting from the late 70s up through the late 80s, where we started to deal more with sampled audio. We will not be discussing sampled audio today. But something I'm sure you guys are familiar with is the character of early video game music, mostly square wave bass. Very limited tones available from these chips. And that's due to economic reasons. Back then, memory and processing power was quite scarce. So to create an affordable consumer device for displaying a video game program and making meaningful audio output, they usually went the way of custom integrated circuits to generate the sound and video. Now, the circuits used to generate this audio were necessarily primitive. They generate square or pulse wave based audio, usually from a divided high frequency clock. There are a couple brilliant things that they do in these designs to make the audio output that much more interesting. But For example, in the Atari 2600 and the Atari 8-bit computers, the custom chipsets would handle some of the more interesting functions of the computers that couldn't be achieved with off-the-shelf logic or memory. So, for example, the sound chips in the Ataris would also process joystick or paddle inputs, generate the audio channels, and in the case of the Atari 2600, output the video signal. So, this Atari 2600 was released in 1977, was a very popular game system up through the mid-80s, had a very interesting way of programming where you there's no real video memory to speak of, so you'd chase the beam, as they say, to generate the video signal. The audio processor was part of the chip called the television interface adapter, and it provided two different sounds through linear feedback shift registers, which is a means of generating pseudo-random number sequences. So this would be clocked by a division of the master clock of the system, and this would be further divided to generate the audio tones, musical pitches. Problem is, in the Atari 2600, the frequency divider is only a 5-bit value, so that's 32 values over so many octaves. So you see that you cannot get an octave of pitches in tune using this scheme. There was once a rock band named Journey, and they licensed their essence to the Data East Corporation, who produced this Atari 2600 video game. Totally different game from the arcade one. But the introduction music to this game is a programmed version of Don't Stop Believing. However, it sounds kind of off using a 5-bit frequency divider. So sometimes companies writing software for the Atari 2600 would ask the programmer to create a little musical tune for the games, but this was very difficult due to the coarse frequency division. As you can hear, the 4th scale degree there in the Journey tune was out there. So a lot of the nice music and sound from the Atari 600 is more rhythmic in nature. So I'll play a couple examples here. This first one's from a game called Yar's Revenge, and this is just some gameplay audio where it has a nice heavy drone, which is characteristic of the LFSR tone generation method. This next one is from a homebrew game composed in the last 10 years called Marble Craze. It avoids the problem of the out-of-tune generations by having a more rhythmic approach to the music. I need the whiteboard eraser if anyone has seen it. All right, so the way that these tones were generated using the chip, you have a master frequency that is divided down from the clock, and that can be thought of as your tone. Like, you can play it back out of the chip as a a normal square wave. But you can also use it to clock a shift register using a system of linear feedback, and that generates some more interesting tones. It sounds like a kind of pulse width modulation, as you can hear in the previous audio examples, more narrow pulse sounds. They are just repeating sequences of digital states. So we start with the square wave. %, duty cycle, but we'll use that to clock a shift register. Let's have a nice 4-bit register here. So the data goes into the shift register, but there is a feedback as well. Some of the bits will be exclusive ORed together, and then that value is fed into the register, and we listen to the output here. So as long as you don't fill it with all zeros, you'll have this infinitely repeating sequence of states. Now, the consequence of doing this in the Atari 2600 is that the shift register approach divides the frequency further. So different tones that you set within the chip are out of tune from the square wave. There are a couple different schemes. Like there's a 4-bit one in there, there's a 5-bit. It's nice, but that and the frequency divider problem makes it very difficult to compose a conventional piece of music using this chip. Now, David Crane, the author of the Pitfall game, designed a very interesting custom chip to solve this problem in the Pitfall 2 game. So the Atari TIA has a 5-bit frequency register. It has 4-bit volume registers, meaning there's 16 possible volume levels for the tones. And then I think 8 possible tones to be selected. So this custom chip for Pitfall 2 is a display processor, includes some video memory, but also has a very clever means of generating 3 voices of music. So if you recall the 4-bit volume register, all this chip does is it feeds bits to this volume register to change the volume, and therefore manipulating the DC offset that is present in the audio path to generate some new music. And the way it does this is kind of smart. It uses it weights each of the 3 channels of music. So you have your lead channel, which has a volume of 6. The middle is 5. And then 4. These are all digitally added together. And you get a 16-bit value that is then used to update the volume register. So the custom chip is generating the tunes on its own time. It's just providing this value to update the Atari's actual sound hardware. So this weighted channel scheme means that you don't have to worry about updating any volume registers or anything, and it plugs right into the system as a cartridge, and it just works. I believe that was the only game that the chip was ever used in. So we're going to listen to a short piece of audio coming out of the same Atari 2600 system from Pitfall 2, but you can hear a nice 3-part harmony now. Atari soon released a line of 8-bit computers and derivative video game systems. The base set was the Atari 800. It used a chip called the Pokey, which was a paddle and keyboard interface device, but also had a 4-channel sound generator that was kind of a superset of what we heard in the TIA. So its frequency divider, you could use it at 8 bits or combine 2 channels for 16 bits. So suddenly you have access to however many frequencies that you would need to generate the music. It also included a couple more tones, and I think this series of computers was a lot more popular in Europe than the US, but a small demo scene also developed at the time where programmers would perform some exciting feats and continually outdo themselves for the most exciting graphics and sound programming. So I'm going to play a couple examples using the Pokey chip. This first one is from the commercial game Ball Blazer, one of a couple games that Lucasfilm did. They hired a bunch of really interesting people in the 1984 to do that, 83 I think, to do this. And this music was composed by Peter Langston. The way this music works is that it's algorithmically generated. The bass line plays, does its own thing, but the nice little jazz solo is it's all algorithmic, and so is the overall structure of the piece. It'll kind of do a breakdown every now and again, and it's different every time you play the cartridge. And of course, during gameplay, the nature of the music changes according to the game conditions. If you're interested in that compositional technique, I believe Langston has written a paper titled Riffology about it. So this next clip is from a demo from 1990 by the Hobbytronic group. They a couple demonstrations from graphic demonstrations from really talented programmers. This one kind of shows off the thickness of sounds that you can get by stacking multiple LFSR tones. And the next clip is by the composer Rob Hubbard. It's a version of a piece that's more popular in his Commodore 64 work, but it also shows to highlight the simplicity of the sound chip's tones compared to that. So, the Commodore 64 is yet another popular 8-bit home computer of the era. Plugs right into your TV and has a dedicated sound device called the SID. The SID is special because it was designed more elaborately as to resemble the synthesizer voice of the time, with oscillators and analog filters and everything. It was designed by Bob Yanis, who later did some of the multiplexed oscillator devices for in Sonic. So the SID kind of imitates what the analog synthesizer does. It has your classic waveforms in the oscillator section, 3 channels of them. There's an analog filter that you can send each of the channels through, envelopes, everything. So when you program this, the registers would resemble the structure of the analog synthesizer voice. So the way they accomplish this using the semiconductor process of the time is kind of funny. To realize resonant filter, you're going to need something resembling an op-amp with positive gain. So for the NMOS process they're using at the time, it really, the filter performance varied significantly from unit to unit. So many programmers decline to use the filter entirely. Emulations of this filter aren't the most accurate. I'm going to play a couple more things from Rob Hubbard, who used the filter quite well in this example. So this loading music is the better-known version of the last example that I played. You could hear some of the channels being switched through the analog filter, choking off the frequencies of the sawtooth there. Commando is also one of his better-known pieces, and in this you can hear his arpeggio technique, a very fast-moving octave arpeggio to give more weight to the sound. At higher modulation frequencies, it gives the illusion of more voices playing. If you can read 6502 assembly, I recommend Googling around. You can find a version of his music routine, which is pretty interesting. It shows how through a couple simple commands he realizes these very elaborate arrangements and still able to run the game at the same time. This last example from him here is from the game Skate or Die, which is notable because it uses a form of sampled audio. Once again, we're manipulating the DC offset that's present in the audio just by managing the volume register with the oscillator turned off. So if you update that fast enough in the right pattern, you can generate a sampled sound. Here it's used for guitar and organ. So you can kind of hear the voice management style used, first of all, to make room for the samples and the accompaniment of the other sound channels that are using the native generators on board.
Who was Rob Hubbard?
Rob Hubbard the question was, who is Rob Hubbard? Rob Hubbard is a British video game music composer. I don't remember his year of birth, but he got his start doing Commodore 64 games. He developed his music driver early on and was very prolific in the mid-'80s. He later went on to be the audio technical director at Electronic Arts. So he composed for a couple other systems then. I believe he is retired now. So, the Nintendo Entertainment System is of course, many of us are more familiar with this system than others. It also has a pretty unique sound generator. This is the sound generator is integrated into the NES's CPU, which itself is a custom 6502, missing the decimal mode. But this one has 5 channels, and it kind of goes back to the primitive techniques of the Pokey. Takes it a step further. We have 2 pulse wave channels on the 2A03. They have 4 possible duty cycles. You have your 50-50 square wave. You got 25%, 12.5%, a very narrow pulse, and the 75%, the 25 with inverted phase. These channels have a 4-bit volume register. There's also a noise generator, which does the same. The triangle channel has no volume control because it is realized by a 5-bit up-down counter. So you have 32 possible values in that triangle state table there, but its volume register is not available because all the volume bits are already used to represent the triangle itself. Noise channel has a 16-bit linear feedback shift register, often used for noise and percussive sounds. It also has a shorter non-maximal configuration, which gives these really nice metallic sounds. There's also a single-bit delta modulated sample audio channel where you basically feed the converter an up or a down command. That's occasionally used in games for sampled drum and other sound effects. So, first I'm going to play a sound from the game Metal Gear. It has features typical of a Japanese style of music composing where the pulse channels are used in 2-part harmony. Some of the harmonic progressions are pretty interesting and don't resemble that of popular music at the time. The triangle channel is usually used to imitate a rock bass style. The noise channels are used for percussion as well. I'm not getting audio out of this. Hold on a second, the audio is not working. No, there's no volume control on the computer. Let's try this one again. Alright, hold on a second while I figure this out. Okay, I think we're back now. All right, as I was saying, the Metal Gear, typical of what Japanese video game developers would include in their music, with the two-part harmonies. And a less exciting clip from the game Battletoads, which this one shows off the kind of grunginess of the triangle channel, since you only have 4 possible volume levels there. Once you take it down to the bass register, where most of the games use it, it has a nice character. You can hear there in the triangle bass that the quantization noise is very forward. Now, eventually, the licensing of the NES it spread out a bit more. So, American, European composers started to write for the chip. This is from the game Pictionary. So you can hear a totally different style of composition here. Something interesting that is done in this one is that the opposite phases of the 25% square wave are used. So if you have these two counterphase rectangle waves that are added together, if you detune one of them, then you get a nice little pulse width modulation effect, because on the 2803 chip, each new note event resets the phase. So that's predictable. So this last one here is from Rob Hubbard yet again. This one shows nice use of the noise channel in its 2 modes. If you listen to the hi-hat like sound, that's the channel that is being used. But you can hear it occasionally switching to the 93-bit mode, so it takes on a much more metallic character. And you can also hear his octave arpeggio technique, and he did several games for the NES, some of them unreleased. And his style is a bit different. He'd usually use one of the pulse wave channels for the bass, and he'd use the triangle as a higher pitched arpeggio. Other games include The Immortal, which also had some really neat audio programming tricks. And he also did Chuck Yeager's Air Combat, but that was unreleased. So, it's also possible to extend the audio performance of the NES with custom chips, like many other systems. There's one developed in-house at Konami, the VRC6, which worked as a memory mapper and additional audio generator. So imagine these 5 NES sound channels that are extended by 2 more pulse channels and a sawtooth wave as well. There are only a couple games that use this chip. All of them were only released in Japan. The one that's the most familiar is Castlevania 3. So I'm going to play a short section of audio from the American version of Castlevania 3, which just uses the 5 sound channels. So the Japanese version of Castlevania 3 uses this VRC6 chip, and as such it has some more interesting scrolling effects. Also the graphics are uncensored, but that's a different story. But here you can, in this version of the music, you can hear the all 8 sound channels being used. And pay attention to the bass, that is the sawtooth channel. Realize kind of like the triangle, but it's just a up counter instead of an up down. And the last audio example here is another section from Castlevania 3, which shows off the power of this 8-channel scheme, where all the extra pulse channels are used for echo and detuning effects. Yeah, the pulse channels have 4-bit volume control. So it's crude, but if the envelope's fast enough, it doesn't feel that chunky. But what a lot of these pieces did in Castlevania, they were using the extra square wave channels, like they're delaying the note events. They're a bunch of like really weird ghost notes, and compositionally it's really interesting to look at. So the MSX is a Z80-based 8-bit computer platform that was mostly popular in Japan, Europe, the Middle East. It had a pretty crude sound generator. The programmable sound generator, the AY3. Derivatives of this showed up in various arcade games, other computer systems, the Atari ST. Its square wave channels, of which there were 3, had a volume in an envelope, noise generator as well. It somehow feels a bit less exciting if you can't get away from the 50% duty cycle. So here's a clip from the original version of Metal Gear that shows the 2-voice harmony style. So you can hear the volume decays there. You can also hear the frequency divider is fine enough to allow for the vibrato effect. Now, the real exciting thing, though, is, again, a custom chip that extends the functionality of the system. In this case, we have another Konami custom chip called the SCC, which found its way into some of the more exciting MSX games. Again, none of this was ever released in the United States. But the SCC added 5 wavetable channels that used really short 32-sample 8-bit waveforms. But the way that these composers put the SCC to use is the wavetable morph was a core part of the composition method here. So though the waveforms are very short 8-bit, lots of quantization noise. There are some pretty dramatic spectral evolutions in the various sounds. So from the game Metal Gear 2, which is my favorite to use this chip, we're going to hear, which one is this? Okay, so in this one, listen for the lead part to come in, but then listen for the spectral evolution. It'll go up to the first harmonic there, and you get a nice octave effect out of that. And that's exclusively used by changing the wavetable gradually. The way they arrange these wavetables were generally to allow for the illusion of a smooth morph, and they're not just fading in another note that is an octave higher. They're accomplishing this by modulating the wavetable. And here's another clip from Metal Gear 2. In that example, you could hear the pulse width modulation in the bass, which is accomplished through more wavetable modulation. These other two tracks are from space shooter games on the MSX, and I chose them because you can hear more dramatic wave morphs. And now this last sound clip is from the title sequence of Metal Gear 2, widely considered to be one of the best 8-bit graphics sequences ever commercially released. But at the end, when the title of the game comes up, it makes this really nice sound that uses up most of the wavetable channels, and it's really excessive. Usually the composer or the company to compose on these systems would, for example, Rob Hubbard wrote his own music driver in 6502 assembly. Most other independent composers at the time had their own custom bag of tricks like that. Companies or their music teams would usually have their own in-house sound driver that they'd write. There's no real pre-packaged arrangement to write music for these sorts of chips. I guess each pioneering composer had to roll their own or use the company's tools. Are there any other questions about these chips or the methods used? All right, I guess not. So this Argos Bleak module displayed on the screen is a 4-channel control voltage quantizer that also enables a lot of the compositional techniques you've just heard. There's a series of inputs on the bottom that allow you to immediately change the flow of the control voltage going in, enable or disable the slew limiter, octave arpeggio. There's also a chord generator up on top. As always, the timbre of your modular tone is an individual responsibility, but this quantizer will allow you to achieve some of the tricks that you've heard in these more tightly programmed video game music sequences. So, a lot of these chips depend on generating square waves. It's the most efficient way of getting an audible tone using these simple transistor circuits. But there are some problems when we want to reproduce these shapes on real-world audio systems. Now, the square wave edge is it's a pretty idealistic thing. You have this nice sharp corner. So there's supposed to be an instant rise up to the maximum and then an instant fall. Things don't really work that way because your speaker cone can't generate a jump event. It has to continuously move from one location to another. That essentially integrates the step event that you're putting into the speaker. If you want to reproduce this square wave digitally, you're most likely going to be in a discrete time sampled system. So there's considerations of the sampling rate. How many harmonics of this square wave can you produce? So let's look at our square wave here. It actually looks a bit more like this in such a system, where you have some overshoot, and then it kind of rings around there. And if we're talking non-causality, we also have it on that side as well. If you'd like to perfectly represent a discontinuity in the time domain, spectrally speaking, you need an infinite amount of information to describe it in the frequency domain. So there are a lot of limitations. Fortunately, with these sound chips, we're listening to the square wave output right out of the device. No digital audio converter, no intervening sampled audio system, so we don't have to worry about that. It usually only passes through a third-order filter before it hits your TV or your speakers, and you're able to enjoy the essence of the sound that much more. We don't have to, well, if you had the system in front of you, instead of watching a YouTube video or listening to an emulation, you didn't have to worry about all of this processing getting in the way. So, this brings in some more troubling behavior when we talk about the accurate reproduction of square waves, step events, and other difficult bits of audio. So, the square wave itself has a rich amount of higher harmonics that eventually wreak havoc with the analog-digital converter in the form of aliasing. It's quite a popular sport these days to avoid aliasing or prevent it, or pretend that your audio signal is something other than what it actually is. So we either try to filter it heavily going into the converter. Depending on the nature of the filter, you'll get these nice little ringy bits on the forward-going segments. Or oversampling, where you run the filter at a higher sampling rate than the rest of the processing, and you're essentially pushing sailboat fuel through the data pipe to pretend that the signal is less troublesome than it actually is. In recent years, this has been taken a bit further, where the accepted practice of generating, for example, the sawtooth wave is a band-limited scheme, where you don't do a naive representation of the waveform, such as this, however your code works. No, you're adding all these squiggly bits onto there already. You're basically cargo culting the Gibbs phenomena right back into the waveform, so it doesn't create any offending frequencies coming out the other side. So, I've designed an audio device that its sampling rate is high enough to not cause a great deal of trouble, but its behavior within that spectrum is quite troublesome. It's standing right up at the boundary, the Nyquist frequency, if you will, and it is behaving badly, in offense to the self-appointed guardians of sonic goodness. So this is the Hertz Donut Mark III. It too was inspired by some of these chip-based sound generation techniques. Thought a lot about discontinuities and hard edges. What I didn't discuss as far as the systems go are the wealth of FM sound chips, such as those by Yamaha, Sega Genesis. A bunch of arcade systems use these FM devices, where frequency modulation is a means of generating a nice series of harmonically related sidebands for a more interesting timbre. So, Hertz Donut has a main oscillator up on top and two modulation operators which run as sine waves. Each operator, you push these buttons to select it, and the display will show the characteristics of that. But these four sliders represent a mixer. You select your source, and then you move the sliders to set the amount that goes to each destination, such as the main oscillator frequency, the other operator, and two different sound modification algorithms. So you set your mix there. You do that for each of the sources. Your three sources are operator A, operator B, and the external input. Then that all goes through this master modulation control to determine the total amount of modulation. And that has a dedicated CV input and attenuverter as well. Up on top, we have your standard oscillator controls, such as your frequency fine-tune, frequency CV, but now there's this fold control. I need a wipe. In the last week, the Hertz Donut's timbre generation scheme has changed quite a lot. In a previous demonstration that I gave a few weeks ago, you'd set the base waveform of the oscillator by holding a button, turning a knob. It would morph from sine to triangle to saw to pulse wave. But that, I don't think that was the most reasonable way of generating harmonics that get torn up later by the wave shaper. There's quite a lot of room to move between the spectrum of the triangle wave and that of the sawtooth. Those two are next to each other, so it just slams it with all the harmonics all at once, and it quickly turns to mush if you're doing a lot of frequency modulation or wave folding. So recently I've been thinking a lot about the Casio CZ101. That uses a pretty interesting way of changing its waveforms. It's also very computationally efficient. So let's look at the way that we generally make a sine wave using a wavetable lookup. This ramp, it represents the waveform value that you want to read from a sine table. So each location on this ramp will look up this value from the sine table. So what happens if you put something in other than a ramp to look up the waveform? Back in the 80s, this was called phase distortion, and is usually done with multi-segment stuff like that. So you see that the slope on this first part before the breakpoint is a bit sharper. That would kind of compress things like that and then give a nice wider trough. And the effect on the ears is that this, as you crossfade from this ramp to this one, you get a linear progression of higher harmonics, not quite as sharp as like the triangle saw transition. It sounds like kind of like the Helmholtz trumpet. And it's much more appropriate for further wave shaping or heavy modulation. Now, of course, on the upper end of things, we get a bit more adventurous. We have things change direction, which introduces even harmonics, or a bunch more zero crossings. I don't know what the sine wave will look like if you looked that up, but we're going to do some listening now. We are now listening to a plain sine wave from the Hertz Donut Mark III. We're going to introduce some modulation from just one of the operators. So I'm going to turn this knob here. The way this works is in the default mode, you pick the modulation ratio, the frequency. So right now we're at 1-1, which means the modulation operator is running at the same frequency, 78 Hertz, as the primary oscillator. Modulation intensity. Let's bring it down a bit. Now I'm going to change it to a 2-1. Actually, I have some modulation in there. Let me get it out of there. I also have some non-integer ones in there. Here's 1.5, which actually gives you the illusion of a division. And here's some subharmonics as well. Now, all these examples were just realized using sine waves on both carrier and modulator. So this phase distortion scheme, we're going to listen to that for a little bit. I'm going to manually turn the fold knob, which will change the shape of the ramp that is looking up the sine waveform. You can hear it get nice and trumpety. Now, as I move it past 12 o'clock, the ramps will get more adventurous. It sounds kind of tame, but if you start adding in some frequency modulation to it, here's some 1-1. Now we're going to move the fold again. There are two other things that we can do to the waveform. The first is also something that's familiar from those old Casio synthesizers, and that is the resonance. By windowing the waveform in conjunction with a synchronized ramp, you can imitate a resonant filter pretty nicely. And that's just coming out of the sine wave table. If you change the waveform while the resonance is happening, it starts sounding more like normal oscillator sync. Turning the resonance off for a bit. There's a third thing that uses the exclusive OR logic to make leaves and branches grow out of your waveforms. It sounds pretty intense. Put some resonance back on that. Back to our normal sine wave for now. So now we'll discuss the technique of building up a complex sound using the Hertz donut. First of all, let's look at all the voices that are available to us. Let's go back to our resonance, put that up so we can hear something with some very limited harmonic action. We'll go into a menu and turn the unison on. This is now running a second oscillator in parallel for that stacked voice feeling, and you can hear the effect more dramatically as you bring in some frequency modulation. Second modulation operator. Use that to modify waveform settings at audio rate. Set it to 1:1 ratio. The mod mixer to start have the operators modulate each other, things can get noisy pretty quickly. As always, you can use the master modulation control to take things back down to a more sensible level. all the parameters of the Hertz Mark III may be stored and recalled as presets. This recent change, the phase distortion oscillator scheme, also has the benefit of making the timbre settings of the Hertz donut completely modeless, so they may all be smoothly morphed when you change from preset to preset, as well as all the settings in the modulation mixer. So I'm going to enable the preset manager and play back a couple sounds. So each preset may have a completely different character that you've defined by setting the mixer levels. And you may easily navigate within that character by using the modulation knob. Preset Manager can also operate in a continuous morphing mode, where all of the knob-based parameters of the voice may smoothly morph from preset to preset with attenuator. So I'm going to plug a nice slow sine wave LFO into that. Now let's bring up the attenuator. So once the modulation mixes and the oscillator timbre are programmed in the Hertz donut, they can be easily stored as presets to be recalled later. I've tried my best to have this thing be made of sweet spots, and the preset memory has 8 slots that can be freely morphed between. So it's suitable for both live patching and playing style or preset-based recall. Does anyone have any questions about how this device works? It's in the display. So you hit the fold mode button until the arrow says that the fold knob is editing the resonance. I'll go back to a simple patch here. So here we are with just our sine wave. I'm going to click over to resonance by pressing that button. Now I'll turn this fold knob. And that, of course, gets programmed and stored as part of the preset, and the resonance amounts morph between presets if you're in that mode. Okay, so signal flow of the Hertz Donut Mark III. We will have our main oscillator here. And we have 2 modulation operators, which are preset to sine. This does whatever it wants. So the mixer sliders here allow you to determine how much of each signal goes where. And this is your, let's call that the wave shaper. That can also go into there. So the mixers are determining the amount of how much the modulation signal goes into each destination. So the main oscillator signal has its own internal timbre controls, some of which are represented by this trapezoid here. And after all the modulation, we're just listening to the output of all that. There is an auxiliary output on the module, which you can set it to be either operator A or B, or the combination of both if you'd like to listen to the sines or use them to modulate other modules that are in tune with the Hertz donut. I also need to add that you aren't restricted to the quantized intervals in the modulation oscillator. You can set them into free mode for more inharmonic results. And of course, if you turn the unison on, that doubles up everything. So you can have a nice 2-voice unison going on. We have a question from the internet asking about if the presets can smoothly morph between fold modes. The answer is yes. Since we changed the phase distortion scheme, the wave folding is modeless. There's no red or green mode. No need to imitate the 259E anymore. So you have continuous amounts of the wave folding, the leaf growing algorithm, and the resonance. Those all get swept when you go between presets with different settings for each parameter. Yes. Umbrage is the leaf growing scheme that I keep discussing. So let's say you have, again, your sawtooth wave looking up a sine wave. But if there's some secret sauce here. If you take that saw wave and exclusive OR it with a bunch of other stuff, like half frequency, triangle, other things. And then if you modulate the amount of that triangle going in, and looking at this in a purely bitwise manner, you get really cool stuff happening, like get really discontinuous activity that has a really neat sounding harmonic relationship, and that causes your sine wave to grow hair in certain parts of it. So the umbrage changes the gain of the other module going into the other waveform going into the logic, which changes your lookup waveform, resulting in a more interesting sine wave. And that fourth slider you see there is the modulation destination for that. I'll play a little bit of that so you can hear what that sounds like. It generates quite a lot of higher harmonics, but they don't make a huge mess, and the sampling rate is 96 kilohertz anyway, so we can do whatever we want without crossing a certain boundary. That's what it sounds like under audio rate modulation. We can also use the fold knob to access that parameter directly. The CV input for fold may also, in the menu, you can go there and assign it to any of the three waveform parameters, whether it's the umbrage, the phase distortion, or the resonance. We can assign the CV input to any of the three wave parameters. That assignment can change from preset to preset. Modulate something now using that. I'll change the destination to resonance. Resonance sounds kind of funny with frequency modulation applied because the way in which we're generating the resonance. Once again, ramp wave looking up a sine wave. But what happens if you have the ramp wave running at a higher frequency that is synced to the sine wave? You can have a bunch of little peaks like that. And then when the period of the original sawtooth resets, you're going to have something like that. So if you use that to look up the sine wave, you're going to end up with a higher frequency sine wave like this, but then there's going to be a jump when the driving sawtooth resets. So the solution to this is to use a downward going ramp as a window. So if you multiply this windowing function by this higher frequency sine that has a little bump in it, that has the effect of removing the bump entirely because the reset point coincides with the 0 that's getting multiplied at the end of this thing. So it looks more like this. It's like more like a naturally resonating waveform. The illusion falls apart at extreme frequencies or under audio rate frequency modulation, but I think it sounds nice as we have it right now in unison. And of course, you can change the distortion of the saw waveform before it gets synchronized like that. And audio rate modulate the change of that sawtooth wave itself. You can't change the amount, the resonance, but the frequency itself changes. Let me get you back to a sine wave here so we can hear it more clearly. Listening to a sine wave now. Now I'll bring the resonance in. So there's always going to be a relationship to the base frequency of the waveform. You're actually increasing the amount of peaks in the waveform as you bring the resonance up, but it sounds like you're increasing the amount to the resonance, but that's just because you're pushing more higher frequency information up into the less windowed part of the sound. Yes, so this is what it sounds like when modulated. And that's independent of the oscillator frequency. Any other questions? On this one, the wavetables are not customizable. We've selected a nice little morph of possible phase distortion functions, but I think there, on the Hertz donut, there are many dimensions in which you can modify the sound. So we didn't put an SD card slot on this one.
Slow people in the audience, can you just go over each function of those knobs again? I just want to...
Okay, to go over the functions of the knobs.
Main oscillator.
Yeah, the big knob here is your main oscillator tuning, and then there's also this little knob here that's associated with it. By default, the big knob does coarse tune, small one does fine tune. If you feel differently, as I do, you can use the menu to swap the functions of the two, and that is that setting can be restored after power down. So you have your typical oscillator controls. You have the sync input, accepts a rising edge to reset the phase of the accumulator. 1 volt per octave input. Frequency CV input with a tenuverter. The attenuverter is stored as part of the preset. Is what exponential? Yeah. It does low audio rates. I think it goes up to 2K or so. Negative voltages are valid. There's the fold CV input and its attenuverter. The function of the fold parameter is determined by clicking the button, watching the display. The display also has a visual representation of mixer sliders for your mixer functions here, as well as the 3 waveform parameters, so you can keep track of what's going on in your sound and if anything needs to be switched off. There's the manual control for the fold. And let's go down to the operators. The operators are more limited oscillators that are used for modulating the various parameters on the unit. So operator A, the big knob selects the multiplication or the division of the frequency, or the frequency itself if you want to run it in free mode. The button simply selects the operator in the display if you want more information about its frequency, which note it's playing, how to tune it. You can also access its menu, which has a limited amount of options. Operator A has a fine-tune control and a 1 volt per octave input as well, so you can slightly detune the sound for more inharmonics or have it play in a tuned fashion as well, which you can access from the auxiliary output. Operator B is a bit more limited. There's an external input which accepts audio signal, 96 kilohertz sampling rate. That has its own selector button as well. So the external audio input as well as the 2 operators each have their own set of 4 mixer settings for getting bus to various parts of the module, such as main oscillator frequency, the other operator's frequency, and 2 of the waveform parameters. The resonance doesn't sound so good at audio rate modulation, so it doesn't have a control for that. There's also a mix output that's a combination of all the different audio outputs there. So if you set the auxiliary output to be a mix of A and B, you can realize some of the parallel algorithms. Like, for example, the DX7 has a couple algorithms where things are mixed together at the end instead of modulating each other in series. You can realize stuff like that by carefully setting up your mixer and then using the mix output instead of the main. The main output is always going to be a series scheme, since we're just listening to the output of that, and the operators come in to modulate it before, where we don't listen to the operator signal directly. To do that, you have to use the mix output.
So that gives you direct audio output to the operators too.
Yeah, the aux output does the operators. And up here in the corner is our standard interface for the preset manager, which is present on all Mark III modules. It has a CV input that takes low audio rate, negative voltages as well, an attenuator or attenuverter. And there are different modes that you can program the attenuator for, whether it's an offset or an attenuator for the preset voltage. You can also set the preset CV input to act as a trigger input for the random patch generator. I'm not demonstrating that today because I'm trying to teach the random patch generator that just because you can do something, you shouldn't. Then there's the rotary encoder for accessing different menus on the module and editing parameters within those menus. To access the menu, hold down the encoder button and press whichever button whose menu you'd like to access. Yeah,
This is not like this is just turn on and then you tell the menu. Okay.
Yeah.
You can't switch them on.
No, but if you want to discontinue their modulation from what you're hearing in the main, you just select the source and move the sliders down. Or if you just crank this knob fully, Wittershins, it goes off totally.
And you're just listening to the main also.
Yeah. And some of the most satisfying sounds don't have any modulation at all, especially if you get a nice thing going between the phase distortion and the resonance. And if you put the unison on at that point, it sounds more like a standard synthesizer sound. Things get weird really quickly if you introduce modulation into that.
How many fold modes
They're just the 3 parameters for the.
Three parameters.
Yeah, 3 parameters are represented on the display. This virtual representation of the display on the screen does not have any graphics in it, but if you'd imagine 3 sliders there, you'd be able to like see an arrow pointing to whichever one you'd be editing by pressing the button and then doing the fold mode. And of course those latch in so you can edit one, switch to the other, and then once you have your bass tone done, you select which parameter you like the CV input to modify. You can store that as a preset and then play around with your modulations if you wish.
So this outputs those outputs.
Yes, you can select.
It's just the 2 sine waves.
Yeah, you can select if it's either or a mix of both.
Nice. Are there any other changes you're going to make over the next week?
I don't think there are going to be any changes as dramatic as what happened last week. I think my tester, hi John, would not like that very much. But right now we're just working on getting the preset manager in order. A couple small bugs to be worked out there. Might adjust the flavor of some of the modulation mix, like the maximum gain possible within each of the slots. It's been a real adventure to think about what nonlinearities should exist in such a scheme when you're not listening to the actual signal that only has an indirect effect through the modulation. It's been a real exercise to come to a mixer character that worked well in the context of audio rate modulation instead of audio that you actually listen to. Things are working great. The developing time was pretty short on this one. Our Mark III platform was first introduced on Piston Honda Mark III, the wavetable oscillator, and a lot of its technology is present here. Most of the code is in the preset section, actually, and it requires the most debugging, just a lot of copying and pasting and making sure that every last parameter is accounted for in all the different modes that the preset manager can operate. When do I expect it to be available? Development should wrap up in the next 3 or 4 weeks. I'm waiting for some custom potentiometers from overseas to get in there, because this one will use nice metal shaft bolted to faceplate pots. I'd probably say 2 or 3 months. I'm not sure what other module I'd produce first. I'm trying to restock a couple things at the minute, but for sure the next new release will be the Hertz Donut Mark III.
What other products do you have coming out in the future? Can you give us any hints about that?
Well, I have I'm using the Mark III technology to wrap up a full synthesizer voice. There'll be double Andre Jr. I'd also like to finish the Bionic Lester Mark III soon, which has mutated quite a bit from its Mark II version that never got released. Now we're running with a fully digital, fully morphable design with independent resonance for each of the channels. Presettable, of course. And if you like things like the Waldorf Microwave XTs, you know, how you could run the wave shaper before it goes into the filter, I think a lot about that. As a matter of transgression, I might make the design about my love of fixed point quantization noise. I don't know. I haven't decided on the final character of the device yet, but I think the end result would be appropriate to use with either of these oscillators anyway. Yeah, we're doing a restock of Stilson Hammer very soon. It has some new firmware that fixes a couple bugs and greatly improves the ease of operating the burst function.
Any other questions?
will there be a Mark III Time Safari? At the moment, there are no plans for that. We're actually going to do a run of the Mark II hardware pretty soon with completely rewritten firmware that will be more immediate and better sounding as a delay, being able to access the pitch shifter without some obscure expander unit that you can't find anywhere. We do have another time domain device in the works that's different from the Time Safari idea. I've been threatening it since 2007, and I think this platform here is the most appropriate way to deploy it. But I'll probably present that one around January or so. I don't have a schedule for the Time Safari production yet. But things should generally become more available throughout the rest of this year.
Anybody else? Oh, another one.
Well, on the main board, we're running with PIC 32s now. I've used various generations of PIC microcontrollers and DSPs throughout the entire life of the company. We typically use the Wolfson codec for audio conversion. And then it's some pretty unadventurous 7400 series logic to drive the interface, like the LEDs, buttons, multiplexers. Mark III series uses these nice 128 by 32 OLEDs displays now, and much more satisfied with that.
As always, it's been a pleasure. Thank you very much. And if anybody has any questions, just type them in after you've watched the video. It'll be up immediately as a YouTube archive. And of course, we'll have this as soon as it's out. And we have a pre-stock of the Piston Honda 3s on Monday, and Stilson Hammers when those come out. And anyway, thanks a lot for joining us, and see you later.